Just like we had properties of matrix addition, there's a bunch of properties of matrix multiplication, which aren't quite as extensive. They don't quite get you because you don't have inverses. These are all the ones except for the fact that you have because not all matrices have inverses. In fact, it turns out that only square matrices have inverses because it's like an inverse is something that you multiply by to get a zero matrix, right? Or the identity matrix. But so it turns out that you can only have inverses when they're square, but all of these properties work for all of them. So let's look and just see what they are. Well, if I want to multiply the product of three matrices, I can first multiply like A, B, and C. I can multiply B and C. They have to be appropriate sizes, right? Like they can be different sizes, but they have to be the right sizes for the product to exist. So if the product exists, then, and I want to multiply A, B, and C, I could do it like first B and C, then multiply A times that product, or first multiply A and B and multiply by this product. But it turns out those two, the parentheses don't matter. I can do it any order I want. I can first do A and B, then C, or first do B and C and then do A. If I want to multiply, if I want to do the product of like this A has been rescaled by R, I can just multiply A and B and then multiply the whole product by R. And the same thing works by here. If I have an R, I can move this R from either outside or from A to B. It doesn't matter what a number just sort of moves through the product. Okay, now, this is not completely trivial because the product itself is a sum of terms. It's like it's like first one, it's like entry, it's like this product, and you've got a sum of terms. So you have to be careful about what all this actually means. It's a little bit less trivial if these are true. Here's one that's interesting. If I multiply A times the sum of B plus C, I can just bring in A times B plus A times C. Multiplication is less distributive and right distributive. I can move the second one in on either side. So it has the distributive property of arithmetic. But that's interesting because it's just not completely clear that this is an obvious thing. And then there's always an identity matrix. The identity matrix, there exists a unique n by n matrix I, that is, such that for any same size matrix, n by n matrix M, there's an identity element that 1 times M equals M times 1 equals M. So I is called the n by n identity matrix. So it's always just an n by n matrix, right? Well, so that if I wanted to have, let's say I wanted to have a matrix A here, and it's M by N, and I want to find a matrix here that equals some identity matrix, right? Well, if this is an M by M matrix, then the problem here is because I have to put in here, this one would have to be an N by M matrix to produce this. And it turns out that we're only going to define this when n equals m. So we're only going to have the case m by m times m by n equals m. We're only going to do it for what are called square matrices. So that's why the restriction here to just dealing with the identity matrix that's an n by n. It's going to turn out that the identity matrix looks like this in general. Like there's a 2 by 2 identity matrix. There's a 3 by 3. So you can see this. Let's say I had 1, 2, 3, 4, and I multiply by 1, 0, 0, 1. Well, that's going to equal 1 times 1 plus 2 times 0 is 1. First row by second column is 1 times 0 plus 2 times 1. Second row by first column is 3 times 1 plus 4 times 0. second row by second column is 3 times 0 plus 4 times 1. And you can see this matrix is the same as this matrix. So it just works out. If this is the matrix you want that performs this task. So these are all the 3 by 3 matrices. This is one. You can see this long thing here. The entries on this long diagonal, if this is the matrix I, these entries are I11, I22, I33. These are all equal to 1. The one where the ij is equal, and all the off diagonal ones, the ones like 1, 2, are all equal to 0. Okay. So that's the context. And then if it turns out that here's the identity matrix written out like the general pattern, and then you can sort of write this out as it's hard to look at the sums because there's so many like subscripts, but you can prove that it's unique also if there's no other matrix that does that. Okay. Then there's other proofs. And you notice here that there's like, it's hard to look at. It's like, but you're doing the same thing. You're just saying, using the identity of this, but you're using that B plus C, this is the different B plus C entries, but with your multiplication, you end up with a sum, and there's some subtleties with dealing with that. So I'm not going to go over here. This is the hardest one. Like, it's like you have to interchange two sums. But it turns out that it all works, surprisingly. And I try to make that motivate that there. But here, let's see what kind of exercises you want to do. Okay. So what you really need to do is be able to sort of look at the additive properties and look at those proofs and do these exercises. For example, in the next demonstration, there'll be a raft of problems like this, where you have to just do, so this one combines products and addition and multiplication with numbers. So this is sort of matrix algebra or matrix arithmetic. And that's basically what you need to do. It's like this problem one here is practice that and be familiar with it. And that's matrix algebra. That is just becoming familiar with it. And then there's other topics. Let me